This is HSC Chemistry tutorial for the sampler module, and this is multi-stage sampling example. This example is from Pitard's book, and we are planning to take samples from the molybdenite ore and for chemical assays. The original primary sample is drill core sample, and we plan to take 20 kilograms primary samples. Molybdenite grade in the ore is 0.167, so it's molybdenite, not molybdenum. The form factor and the granulometric distribution factor, we use typical values of 0.5 and 0.25. Molybdenite grain size is 500 microns, its density is 4.7, and the density of the sample or the ore is 2.7. The planned sample preparation consists of 4 stages. First of all, we take the 20 kilogram sample to minus 25 millimeter. Then from this we split and take it 2.5 kilogram sample further to minus 3.35 millimeter. This is split, and we take 625 grams of sample and ground it to minus 0.71 millimeter. Now this is further split, and 150 gram is taken and milled to analysis fineness minus 100 microns, and finally 1 gram is of that pulverized sample. From that, one is split so that 1 gram is taken for the chemical assay. And the question is what kind of sampling error we will have if you use this scheme, and our target as the sampling error would be less than 5%. So we are going to check that. And for that, we use HSC Chemistry to calculate the sampling error. So we are moving now to HSC Chemistry and the sampler module. And we take here multi-stage sampling. And actually this example can be loaded by pressing example button. But now we are going to work from scratch, so therefore I'm reloading this window. Size of the lot primary sample is now 20 kilograms. And then form factor, we click here text and select common value from factor. For the granulometric distribution factor, we click again and select from list common value. Of course, we could have put this manually. Then grain size of molybdenite 500 microns. Then molybdenite content in molybdenite, it sounds a bit strange, but it's 100. So if we would work with molybdenum grade in the ore, then we should put here a molybdenum content of molybdenite. But we have worked out how is the grade in terms of molybdenite. It's 0.167, and then for the density of the mineral, we could look here a list, but we don't have molybdenite, so that's why this is 7. Directly typing 4.7 and the density of 4. And here and write text which is to be shown then in the key diagram. Okay, base information we have put checking seems to be alright. Then pressing this table button will take us to the next step where we define sample particle sizes and then the sample size. So to generate this table, right size table, we put here that the sample steps, there are 4. And now we are solving overall standard deviation of given given particle sheet, and pressing OK here now generates a table, and this white here indicates that this is where we should where we need to put values. So we work from particle sizes to the sample sizes this way, and then next row, and finally. So the first step is particle size was 25 millimeters, and from that, so that was 20 kilograms, 25 millimeters. From that, we are going to take 2.5 kilogram sample. That is further crushed to 3.35 millimeter, and then we split to 5-gram sample, and that we take 0.71 millimeters, take 150 grams sample, and finally pulverize 0.1, and that is 1 gram. And we put here that the analysis error is 0, so we now exclude the analysis. Now we are ready to find what kind of error this sampling machine gives, and we press now solve button. And to our shock, we find that actually the sampling error is much higher than we expected, 52.77%. Checking now the G diagram, the next page, or by pressing the button, we can see, so G diagram now shows on an XY how the sampling procedure goes on. On x-axis is the particle size, and the y-axis we have a sample weight. Original sample is here 20 kilogram, and from that, in a particle size of 25 millimeters, get this sample of 2.5 kilograms. And now these diagonal lines or curves indicates the error, and 5 is this blue one, and from blue one this way the sampling error increases. So we should not cross this blue line if we want to keep all the time above 5. So here we go well below blue line. Now we get back when reducing the particle size, we get black here, the safe side, but this next sample is too small if this would be the particle size. But the two last steps seems to be all right. We need to revise this, and we could do by checking this, do it graphically here, that to design the sampling scheme that we are on the safe side, so above this blue. But we can do it also analytically. We get back to table, and now we change the problem so that we change the sample sizes, because our equipments which are available, jaw crusher, swing mill, ring mill maybe, this will give these particle sizes. So we don't want to change the equipmentation which we have. We want to only adjust these sample sizes. That's why we change the problem that we estimate the sample sizes for given particle size. And now we just need to put here the max acceptable error, total error, sorry, it's 5. And now we can press solve button here, and now we will get a balanced sample preparation scheme where our total error is 5, and each step has low error to relatively 2.5. Now getting back to G diagram, looks good. we are all the time on the safe side of this blue one, but these first steps seems to be a bit ridiculous. We are taking now from 25 kilograms, 20 kilogram, 20. So this seems to be unnecessary steps. We could work directly so that we take this sample of 3.5 grams, millimeters. So what I'm going to do is that I'm redesigning it to include three stages and analyze error 0, total 5, and therefore we are taking the full 20 kilograms to 3.35 millimeter, and then we take about half a kilo in that particle size, take it to 0.7, and then we can take 150 grams or even a bit less. And finally, from the pulverized sample, we don't even need to take 1 gram. We can take about half of that. So now we have revised the sampling sheet, and we can now go on to prepare the sample with using this scheme, and then we can be sure that the assay results which we get do represent the original primary sample, and therefore we don't have a big risk in our results estimate when using this sampling